So today we will see a very important topic, or I can say we are entering into the core topics. Okay, so airfoil and wing. So in this session we will see the introductory part of the airfoil and wings. What are the nomenclatures of airfoils? Then what are the coefficients of that airfoil and the wings? And what are the aerodynamic coefficients? Okay, so here we will see only look into the introductory part, and we will look more in deep about that. Okay. So first, before proceeding, we will see what are the classifications of aircraft, and based on the classifications of aircraft we will move forward with how to, or what are the types of airfoils used in different kind of aircrafts, or the wing configuration for a different kind of aircrafts. Okay, so because as I've said, in GATE we always look for an application based and the purpose of that applications. Okay, so basically the aircraft can be classified in two types. Okay, heavier than air and lighter than air. So heavier than air can also known as the aerodyne. Okay, heavier than air known as the aerodyne, and lighter than air is known as the aerostat. Aerostat. Now this heavier than air and lighter than air can further classify in two forms, is that non-engine and with engine. I can say with or without engine. Okay, so if I look into without engine, we can also see some of the classifications like kite, then glider and sailplane. Okay, and with engine we can see again this heavier than air can further classified in another significant 6 different types. Okay, 6 different types. First one is a fixed wing, vertical takeoff and landing, then surface effect, then fourth one we have the ornithopter, then fifth one we have rocket propulsion, and sixth one we have the rotary wing. Okay. Now looking into that, another fixed wing further classified in land plane and sea plane. Land plane and sea plane. Sea plane again further classified into the terms of amphibian and the floaters. Okay. And here rotary has been further classified into gyrocopter and the helicopter. So you have to remember this simple tree, right? Now coming into this lighter than air, okay, which is also known as the aerostat, again it can be further classified with and without engine. Now if I say without engine, or I can say non-engine, is known as a free balloon and kite balloon. Then next comes to the with engine, yes, airship. Now airship also I can further classify some. There are in olden days there are some airship which is even without engine, even in fact, right, you might be knowing. So again it depends how you classify on this. Right. Now what kind of expected question you can get from here? So from this particular topic they will give you the couple of the name of the aircrafts. Okay, here they will give, for an example, they might give you maybe like land airplane, amphibian airplane, helicopter and airship, right? I have given the options like land plane, then you have amphibian, then you have gyrocopter, and we have the airship. Now from these options find the odd one out. Okay, now which one will be odd one? Here all other are the heavier than air except the airship. Airship is an lighter than air. So you have to pick the airship. So you can expect such kind of questions from this flowchart. So moving to the next is, before entering into the core what is an airfoil and wing, we will see what are the basic nomenclature of the, or I can say, the parts of an wing. Okay, parts of an aircraft. Okay. So all of you know, but it's just for recapping and what are the working function of the particular aircraft. Then we will move for the airfoil and wing. So you can see in this, in front of you, you can see the three view of aircraft. Okay, this is the front view, this is the top view, and this one is a side view. Okay, front view, top view and side view. Right, now you know the along the length of the fuselage, what is the length of your fuselage? This is the from nose to tip, nose to tip. So when you are moving from nose to tip, this zone is called as a fuselage. Okay, what is the place of fuselage? Where maybe you can place down the cargo for transportations, maybe you can load passengers, the number of passengers you can occupy, right? If it is a consider fighters, the fighters, they will be having the number of missiles or kind of other kind of subjects, right? Okay, so based on that, what is fuselage? Fuselage is a passage where you can or you can say it's a passage where you can it can take up some amount of load. Okay, and also it is a passage where you can keep some kind of mold where you can align the landing gear also, right? Because mostly in the long or the large aircraft you will have the retractable landing gear. So mostly the retractable landing gear will be having the port in the fuselage only. Okay, we'll have the port in the fuselage only. So you will have some passage to carry down all kind of transportation things. Okay, now moving next is a wing. Okay, now we mostly never say the right wing or the left wing. Okay, you might be knowing we never utter this word called as a right wing or left wing. Instead we use some kind of terminology called port and port wing and starboard wing. Okay, port wing and the starboard wing. We never use that right wing and left wing because it depends on the human perspective, in which view the person is seeing, right? So we never say which is right and left. We always use port and starboard wing. Now if I look into the top view of an aircraft, so I can say this one is a port wing and this is the starboard and this is the starboard wing. Alright, so remember, if you don't know, please do remember, there is a port wing and there is a starboard wing. Now in this wing, what are the components you have? Basically you have the flaps. Okay, you will be having the flaps, then you will have the ailerons, then you will have the spoilers. Okay, you might have the flaps, ailerons, and you have the you have this, right? So what is flap? Flap is a high lifting device which just initiate or it add on the some amount of lift. So when we are deflecting the control surface, so aileron is one of the control surface. Okay, the same way we have on the starboard side. Same way we have on the starboard side. Now when the flap is deflecting downwards, both the flap will be deflecting simultaneously. Okay. Now what happens in the aileron? What happens at the aileron if the starboard, okay, if the starboard aileron deflect upwards, if the starboard aileron deflect upwards, what will happen with the port? Port will be deflecting downwards. Now if I have to draw from the front view, I can say that if it is deflecting upward means, let's draw like this, the starboard is deflecting upwards and the port is deflecting downwards. That is a differential way it will be acting. If the port is deflecting upwards, then starboard will deflect downwards. Now what happens here? In this control surface, using this aileron control surface, we can make a movement of the aircraft. And what kind of movement? We can make the movement is a rolling movement. We can make an rolling movement. So how this rolling movement can initiate? When the free stream air hits along the surface, right? So first when the flow is coming, it is hitting over here, it is striking over this particular surface which is deflecting downwards. Now when this force is undertaking with this particular surface, what this object will do? It will try to create a force on this direction, right? It will try to lift up on this direction. And what happens on the other side, port side? If the deflection is in the upward, so when it is over here, the flow is hitting over this particular surface, it will try to create a downward force. Due to this differential form, so the rolling will occur from your front view, the rolling will occur from port to the starboard. Can I say the rolling will occur from the port to the starboard because of this phenomena? Now if I make a reverse case, similarly what will happen? Then it will move, can I say, from my front view of the aircraft, the rolling motion will be in the clockwise direction if I make in a reverse way. That means if I say the starboard is deflected downwards and the port is deflected upwards, then what will happen with my rolling motion of this aircraft? It will be in the clockwise direction. Okay, but in this figure it is an anti-clockwise direction. It is in anti-clock, or you can say counter-clockwise direction, right? Now this is for the aileron, that aileron which gives a rolling movement. Next we have, let's move to the tail section. Okay, tail we have we have the vertical stabilizer, another one we have the horizontal stabilizer. Okay, now in the horizontal stabilizer what we have? We have the another control surface called elevator. We have the elevator. Now here it is unlike aileron, it is not same as aileron. What happens here? If it has to deflect the starboard and the port side, both will be deflecting in the same direction. Both will be deflecting on the same direction. That means what will happen? If the elevator deflects downwards, the nose, if the elevator, let me draw over in the side view, let's consider the elevator is deflected downwards. What will happen? On that case, the nose will also deflect downwards. That is called as a pitch down movement. Okay, it's called as a pitch down movement. If the elevator in the upward side, what will happen? The nose will move up. Okay, so that is called as a pitch up movement. So using this elevator, what we do, we control the pitching movement. Either we can pitch up and pitch down by changing the elevator up and down deflection. Okay, and here both the elevator deflect together at the same angle, deflection. Next we have the vertical stabilizer, where we have the call as a rudder. Okay, rudder control surface. Now using the rudder, what you do, here is a rudder. Now same here, the rudder, either it deflects right and left. So if the rudder deflect on the towards the port side, the rudder has made towards the port side. Now what will happen? What will happen with that aircraft motion? Then in that case, or I can rather draw in this top view, if suppose for an example it has made in this way, right? So all the air when flow and comes over here, it will hit over this particular surface, right? It will create a lift along this side. If it creates to push on that side, what will happen with the nose? Nose will tilt over here. Nose will tilt over here. So yaw movement takes place, that means nose will move towards the port. Simultaneously, when this rudder will move to the opposite direction, nose will move to the another opposite direction. So using the rudder, we make an yaw motion or yaw movement. Either the nose can move on the right and the left from the top view perspective. Okay, from the top view perspective. So in some of the gate question also, they are asking a very simple question like that. So they will give you, describe you in terms of starboard and port wing or other control surface. So accordingly you have to answer, you have to understand what they are asking, and based on this same concept you have to answer it. Now spoiler by the name itself, it says it spoils. Now what it spoils in our aircraft? It spoils the lift, okay, and increase the drag. It spoils the lift and increase the drag. So when we need the spoiler? Obviously we need the spoiler only during landing, okay, because it is coming at high speed. To decelerate the speed, right? So we use the spoiler to decelerate the speed during landing. Okay. Right. Now coming to the very core topic, that is an airfoil and wing. Now before studying that, you must know what is airfoil, right? So you know, we have seen the nomenclatures of this complete aircraft structures, what are the basic components we have. Now if I want to cut any one of the section of the wing, we can see a well defined streamline pattern, and that particular streamline profile is called as an airfoil section. The streamline profile which we see is that a airfoil section. Now we will see more in detail that how to justify the airfoil, what are the types of airfoil, and how the force generate, how this airfoil structure helps to develop the lift, where will be the center of pressure, where will be the CG location, where will be the aerodynamic center. Now here that airfoil which you can see, we are discussing only for the subsonic speed, only for the subsonic speed. Now what happens if I increase the speed? Can I use the same kind of airfoil or not, and why we can't use that also we will look into more in depth. Okay. Now coming to that selection of airfoil. Now to select, we know the cross section of the wing is called as an airfoil. Now what will be the nature of the airfoil? You can see there are lot many A, B, C, D are there. Now which one will be suitable for which flow environment? Okay, so which one will be suitable for which kind of flow environment? Now here when I talk about flow environment, it says that what will be the free stream velocity, or I can say what will be the flight Mach number. What will be the flight Mach number, right? So can you guys able to follow? I am going very fast. You can just let me know.
It's fine.
Okay, fine.
It's fine now.
Okay, all right.
We are able to follow.
Okay, all right. So, yes. So, this velocity play a very important, or you can say the flight speed play a very important role for selecting the appropriate airfoil. Okay. Now, why we need to select? Now, you can see A, B, C, D, right? So, each of this, all are the different kind of airfoils. All are the airfoil, all are the cross section of the wing. Now, which one will be suitable for which kind of flight velocity? So, that for that, and not only that, what should be the thickness to chord ratio? What should be the thickness of this airfoil? So all those things, characterizations of how this characterization of this airfoil can create lift, drag, and other so on parameters. Okay. Now aerodynamics, if I okay, now this can be classified in various kind of flow rhythm. Okay, first is a starting is a subsonic. Okay. This is irrespective of any kind of compressible flow or incompressible flow, that is a secondary. Now we are going just a basic or overall of the flow region. Okay, subsonic, then we have transonic, supersonic, and just consider hypersonic too. Hypersonic. Now let's consider the first airfoil. Okay. Now which among this flow region will be suitable for this first airfoil? Which flow will be suitable? Or if you are designing any kind of aircraft, which one will be the apt for this one, the first one?
For the first one, it's subsonic.
For the subsonic. And why so? Why you are choosing the first one for the subsonic?
It is a symmetrical airfoil and the camber is 0.
It's not because of camber, and the camber is 0, not because of symmetry. You are seeing the blunt surface. Okay, you are seeing the blunt surface, and if you look into the other one, you can find out these are the conical in shape, or I can say sharp leading edge, right? So
yes,
this airfoil have that, this is a blunt and trailing edge is sharp, right? So because of blunt we are using, it can be symmetric, camber, it is irrespective of that subsonic, but we have this blunt because when the flow will come and hit, it will create a very streamlined flow. The main motto is it will create a streamlined flow. And why we prefer to create a streamlined flow? Because we don't want any sort of drag occur on our aircraft. We don't want drag. We just want to lift, and which will help our aircraft to fly and propel forward. We don't want drag. So this streamline will help you to create or create lift and avoid the streamline flow and avoid drag. There won't be any vortices. You don't want any vortices until and unless you keep on increasing the angle of attack. So again we'll recap what is angle of attack and what is the nomenclature also. Okay. Now if you want to increase, now this is for the subsonic case, right, when the Mach number is less than 1. Now what will happen if I increase the Mach number? Let's consider I am taking this Mach number at the 0.99, which is equivalent to sonic speed. Okay. Can I use the same airfoil? Can I use it? At some extent I may use it, but it will cause a bow shock wave, right? It will cause a bow shock wave, right? If I want to use Mach number more than transonic or in supersonic, it will cause a bow shock wave. It will create some kind of high pressure zone ahead of this leading edge, blunt leading edge. And what it can do, because here it will cause a high pressure, it can lead to a damage of the structure. If the structure is damaged, then my flight will become unstable, right? So I cannot fly this profile, okay, this kind of blunt surface kind of profile, I cannot fly in this transonic to hypersonic. So each and every, so how I can overcome this bow shock wave? The bow shock wave can be either overcome within sharp leading edge factor, which we can see for the B, C and D. So B, C, D profiles are quite suitable for a supersonic flow when the Mach number is greater than 1. When the Mach number is greater than 1. So what happens when the flow comes and heat and flow over this particular foil? Okay, it creates an attached flow, right? So obviously when it is moving at more than supersonic or transonic, it has to produce some shock waves, right? But shock waves we have to see whether it is attached or detached. Okay, so we prefer to have an attached shock wave. Attached shock wave is much healthier than the detached shock wave. Okay, so why it is healthier and not healthier, you will know more when you are studying the more in detail about the shock wave, how the pressure changes from one region to another region. All right, so that time you will know the different kind of shock waves it can form. Clear? So the selection of airfoil, the main criteria is a flight speed. Now we will look into that what are the nomenclatures. Okay, now before the nomenclatures, how the lift produce, a basic recap. So which one is a suction side, which one is the pressure side, pressure surface or the suction surface. Okay, so usually the upper curvature part of the subsonic airfoil. So do not forget, here we are discussing about the subsonic airfoil. Okay, so when the upper curvature, okay, is known as the suction side, the lower curvature however forms it, okay, lower curvature is called as a pressure side. Okay, pressure side, that means where we say suction side, where we have the very low pressure, low static pressure. Okay, because bottom we have the high pressure, top we have the low pressure. So high pressure to low pressure, then only the lift creates, right? then only it helps to generate the lift in the wing. Okay. So wherever the pressure is high, what will happen with the velocity? The velocity will be low, and wherever the low pressure, the velocity will be high. Alright. Okay, coming to the airfoil nomenclature, what are the nomenclatures of the subsonic airfoil? Okay, so let's get into the next slide. Alright, so these are the basic nomenclature. The leading edge, first is a leading edge, right, where the air come and hits over here is a leading edge, then it moves at the rear part, right, that is a trailing edge. Then if I want to join a line between the leading edge and the trailing edge, is the line or the length is called as a chord length or the chord. Okay, chord line or the chord, and or the mean distance between the suction side, the upper side is called as a suction side, this is the pressure side. So the mean line or the curvature we call as a camber line, right, the camber line, the distance of the camber from the chord to the mean camber line is called as a camber, and the distance, the maximum distance of the lower curvature and the upper curvature is called as a thickness of the airfoil, is called as a thickness of the airfoil. Okay, so here whatever we have discussed is all about the subsonic. Now I have one question, that if we know this is a leading edge and this is the trailing edge, right? Alright, now if I just make it reverse way, like I just want to make it in this way, something in this way. Now can I say, and the flow is coming along this side, and can I call this as a leading edge and this as a trailing edge? Can I name it? Can I name this? You got my question? Now usually what happens when the air hits over here?
Sure, ma'am.
Yes, I didn't get your question. I didn't get it.
I'm not sure. I'm not sure, ma'am. If suppose the airfoil is being placed in the opposite direction to the free stream air, and I'm not sure whether it will be called as a leading edge, ma'am. The leading edge cannot be changed, ma'am. It has to be the frontal part.
Why it can't change? Because the name itself, it says na leading. That means ahead of that. So what makes it cannot change? Can I make it? Or anything else is there behind leading edge and trailing edge?
Ma'am, it must be having like a rounded surface in the beginning.
Rounded surface in the beginning and small surface in the trailing.
Like, ma'am, I'm not sure with this question, ma'am. I'm not sure with the answer.
Okay.
Ma'am, we can state that, ma'am. If we place the airfoil in an inverse manner, we can say the point where the free stream velocity hits the airfoil can be termed as a leading edge, ma'am.
All right. Let's look into the answer. Okay. Let's see. Let's read this statement. If the leading edge is round, it is described by the polar curve, and therefore it is definite radius of curvature. Okay, and this is here the curvature of airfoil shape is the greater aside from the trailing edge. The trailing edge may be sharp or may be very small in radius of curvature or the bluntness. So this is the definition of the trailing edge, where we will either it can be have very negotiable radius of curvature, or it will be very small, right? If I want to draw a small circle over here, and if I draw another circle over here, right? So which radius of circle is more? So wherever the radius of curvature is more, that particular place we call as a leading edge. Okay, where we have the large we call as a leading edge, where we don't have, where we have smaller as compared to the other one is called as a trailing edge. And that's the reason why we don't have any sort of leading edge and the trailing edge in kind of wedge shape, where we have seen in the supersonic airfoils. Can I say which one is a leading edge and trailing edge? Both are the almost sharp leading edge, right? Both are the sharp leading edge. Can I say define from here? Now based on this statement we cannot say that which one is a leading edge and which one is a trailing edge. Alright, so leading edge, this is in subsonic, leading edge and trailing edge only we can define, right? So leading edge is where the radius of curvature is more, and here it's small. Okay. There was one question in GATE. They asked, they gave some kind of statements and they have asked which of one of the following nomenclature follows with airfoil. Okay. Alright, now coming to another very important thing is that what are the NACA airfoil series. Okay, there are lot many airfoil series are there, but that is not our concern, but the most important concern here is a NACA series. And you should know the full form, all of you know the full form of this NACA, National Advisory Committee for Aeronautics. Okay, before the name was different, it was NASA. Okay, National Aeronautics and Space Administration. From there they have changed to NACA, that is a National Advisory Committee for Aeronautics. So we have some 6 different kind of airfoil series: 4 digit, 5 digit, 1 series or 1 6 series, 6 series, 7 series and 8 series. Okay, so it is very important to remember this first 4, okay, and its application. The first 4 and its application, where it used and how to find out the nomenclature for that. Okay. Now let's look into it. The 4 digit series, what it represents. Okay. So this NACA, this is the first one, second one, third and fourth. Okay. So in this 4 digit series, always into the last 2 digit, always in the last 2 digit you can find out the percentage or the thickness to chord ratio. Okay, that means if this is a airfoil, that means you can find that what is the maximum thickness to chord ratio. Okay, it is a max.
For free fire.
Yes, any question? Alright. Okay, so always the last 2 digit represents the thickness to maximum thickness to chord ratio. Now second, in the 4 digit series, the first one represents the percentage of maximum camber. Okay, percentage of maximum camber, and the second digit explains the location of maximum camber from the leading edge. That means at what point is the maximum camber. Okay, at what point is the maximum camber. That means it is an airfoil, right? So this is the chord line, maybe this is the camber line, and this is the position where we have the maximum this is the position where we have the maximum. So how much distance from the leading edge? Okay. Now let's look into one small example. Let's consider 2 4 1 2. Okay. Now what does the last two digit represent? Always 1 2 3 4. Okay, 4 digit. So last two digit represents the how much amount of thickness to chord ratio. So combinedly 12, that means 12% is a thickness to chord ratio, or I can also write in this way that thickness, maximum thickness is 0.12 of chord, or I can also write maximum thickness is equal to 0.12 of chord. Okay. Next is a fourth one is a location of maximum camber. We have 4. That means we have the 40%. Okay. Whatever the value will be there, you have to multiply into 10. Whatever the value will be there, you have to multiply into 10. That will be the value of your maximum camber location from the leading edge. Now in the question they can ask you in the inverse way. Okay, that means they can ask what will be the maximum location from the trailing edge. Now if the complete length of that thing is 100%, if we are getting 40% from the leading edge, then if they ask from the trailing edge, that means it will be from the 60%, right? So they can ask you in the reverse pattern also. So be ready with anything, any sort of question. Alright. Now first digit represent the maximum camber thickness. Okay, maximum camber. So maximum camber, whatever the value will be, exactly that much amount of percentage. Okay, at that much amount of percentage. Right. So next comes the 5 digit. So 1 2 3 4 5. Again the last two digit represents the maximum thickness to chord ratio. So whatever the value will be there, that will be the percentage of that. The third one represents whether the camber is simple or the reflex, right? Whether it is simple or reflex. If the value, the third value, it can either be 0 or 1, any one of it. It won't be beyond 0 or 1. So if 0 means it is a simple one, 1 means it is a reflex one. Okay, so they can give you the statement and they can ask the find out the possible phenomena of that particular airfoil. Now one more thing before that, if you get some kind of Naka series of 0015, right, that means you have 1 and 2 value is 0, that 1 value and 2 value, first and second digit are 0, then that means it represents your particular airfoil is an symmetric airfoil. Okay. Now moving to the next is a 5 digit series. So last two, as I have said, is a percentage, maximum percentage, that is thickness to chord ratio. Third one represent that whether the airfoil is simple or reflex. It can either depends on 0 to 1. If 0, simple. If 1, it's reflex. Second one represents the location of maximum camber from the leading edge, as we have seen there. Now how to find? Whatever the value will be there, you have to divide by 20 and that will be the percentage of that. Okay, and here one more parameter we'll see in the first digit, the coefficient of lift. Okay, uh, uh, lift coefficient. Okay, so whatever the value will be there, if suppose here you have 3 into 0.15, that amount of coefficient of lift, that is a design airfoil. Here you are going to find the lift will be the design lift, that is small l, C suffix small l. Now let's see one example how to find out for this parameter. So here we have 1, 2, 3, 4, 5. Last two represents the maximum thickness to chord, that means it is of 12%, or I can also say it is like that 0.12 of C of chord. 0 represent it is a simple cambered. Third one represents how much, that location of maximum camber, location of maximum camber. Now if I put 3 by 20, whatever the value will I get will be the alright. So you have to divide by that 20. So whatever the value will get in terms of 0.15 turns of C, that means you are getting 15% of chord. You are getting 15% of chord, right? The first one represents the how much amount of CL, that is a design, this is a design coefficient of lift for this particular airfoil. Okay, so whatever the value you have into multiply 0.15, whatever the value will get will be the amount of CL. Okay, with the CL. Now one digit series, how to find one digit series, and here compare with a 5 digit series. Here whenever the first digit will be represented with 1 and there will be hyphen, that will define you the first digit series. Okay, so again here the same, here they have given 1 first, x, that's considered 2, 3, 4, 5, 6. Let's consider in this way. So last two digit always represents the percentage of maximum thickness to chord. Fourth one is whatever the value will be there, multiply into 0.1. Okay, here the second one, the third one is a hyphen should be there, hyphen should be there. The second one represents the minimum pressure area distance in minimum pressure area distance in 10% of chord. Okay, and the first one indicates the series. Okay, so let's look into example. I will show you one example of the 6 series. I think we have kept 6 series. Alright, now before that let's see what is 6 series. Now you can see there will be having 1, 2, 3. Here again should be hyphen 4, 5, 6. The last two digit represents thickness to chord ratio. The fourth one represents same as first digit series. Now how you represent first digit and sixth series? You must have the first digit as 1, means first series. If you have sixth one, if this one is 6, that means a 6 series. Okay, then fourth one is same, coefficient of lift. Third one represent the coefficient of drag. You just need to multiply 0.1 on both. Next you have the second digit, same as the previous one, minimum pressure distance. Okay, or the 100% 10% of the chord, or 0.1 you say, both are same, then first one indicates the series. Now let's look into it how to find out the parameters. So 1 2 3 4 5 6. Now since it is the first digit is 6, I can say that this is a 6 series. Now second digit represents the minimum pressure area. Okay, either I can say whatever the value into 0.1 times of C, or I can just say the 10% of chord. Both are same. So I can say 1 is there, I can say 10% of chord, or I can say 0.1 of C. Okay, 0.1 of chord. Both are same. Whatever the value will be given, 2, 3, whatever the value will be given, you just multiply, you will get the value. Coefficient of lift, here we have 3 into 0.1 will be getting the value, right? Obviously the last two digit always the same, always represent the thickness to chord ratio. That means it will be 15, or I can say T max equals to 0.15 of C. Alright. So these nomenclatures are very important. You can expect a question from that. Not only like open statement question, they will give you maybe to find out the lift, they will give you the dimensions, and you know what is the lift formula, L equals to half rho V square SCL. They will give you the area, they will give you the velocity, they will give you the density, right? They will give you the airfoil. Simply they will give you the airfoil, the nomenclature of the airfoil. Now using that, either it is 5th series or 6th series, you can find out the lift coefficient. You can find out the lift coefficient from that. So you will know what will be the CL value using the nomenclature. So apply over here, you will get the how much amount of lift will be undertaken by this particular airfoil. Okay. So always remember, GATE, they will never ask you a direct question. Always they will ask you the simple thing in a very twisted form. However, the possibility they can have to ask you in a twisted form, they will ask. Okay. Next, we will see the application. Okay. So, what are the possible applications that we can see in 4, 5, 1, 6 series and 6 series and 7 series. 7 series is not that important, but yes, these are the important ones. Okay. Highly recommended one. So you can see the 4 digit where they use horizontal tail, supersonic jet, helicopter blades. So remember always the symmetrical profile, symmetrical airfoil section, symmetrical 4 digit airfoils are used in horizontal tail, just like they might ask in this question also, that is NACA 009, NACA 0012. These are the profiles are used in horizontal tail. Okay, mostly these are the profile are used, and most of the helicopter blades they are using NACA 0012. Okay, alright. So here now the shrouds and all, they use a cambered airfoil mostly, and that varies, completely varies. And but horizontal tail and helicopter blade, they use a symmetrical airfoil, and these are the airfoils. Now coming to the 5 digit series, they mostly can find using in the cross section of the wing, mostly in the wing, any kind of wing. If I consider passengers, business jet, right, transport aircraft, bombers, right. So these are the aircraft mostly where they use on the wing section they use. Now 1/6 series mostly they use for the aircraft propellers. Okay, the 1/6 series mostly it is efficient in the aircraft propellers. Now 6 series, most of the 6 series it's used for an supersonic jet, or if it is within the range of transonic or beyond the supersonic, then only we prefer to use a 6 series. Okay, 6 series. Now we will see the combination of thickness to, alright, so you can see some of the name of the aircrafts are there. Okay, and each aircraft, what are the kind of wing profile they have used, their twist angle not that important, but if you are interested in that, you can remember this twist angle. But you can see both in the horizontal tail and the vertical tail, most of the cases they are using NACA 0009 and NACA 0012. Most of the cases they have used. Even Northrop, you can see Boeing, if you see Lockheed, if you see Cessna, if you see, right? Alright. Now, okay. Now one more category is there before moving to that aerodynamic characteristics. Okay. I think I missed one slide. No worries. Alright. Now one more category is there, thickness to chord ratio. What will be the percentage of thickness to chord ratio? So if it can be again further classified in 3. If the flight is at an supersonic, okay, supersonic, the thickness to chord ratio should range 3 to 6 percentage. 3 to 6 percentage. If it is an transonic speed, okay, transonic speed, it is preferred to use that 12 to 9 percentage, and sometimes even 6 percentage it can go. If it is at low speed, very low speed, 21 to 15 percentage. 21, these are the thickness to chord ratio. These are the thickness to chord ratio I am talking. Okay, so based on the speed, again the thickness to chord ratio again varies. So more the low speed, more the thicker will be the airfoil, and more the high speed, the thickness to chord ratio will decrease. This is the concept. More the high speed it is moving, the thickness to chord ratio will gradually decrease, and more the low speed, the thickness to chord ratio will be more.
Excuse me, ma'am.
Yes, please.
For low subsonic airfoils, what will be the value of T by C, ma'am? Low subsonic.
Yeah, it will be
50 to 100 meter per second.
50 to 50? No, 21 to 15 percentage.
No, I told about the velocity, ma'am. 50 meters per second to 100 meter per second. I just told velocity.
50 meter per second to 100
meter per second.
Okay. Now if you are
low subsonic,
very low subsonic, see, now this is the speed of the flight. Okay. Now see, there are lot many concepts are there to select that which kind of airfoil. Now if I only by the speed I cannot judge. If you are thinking in the perspective of design, okay, now I have to think
yes,
that whether I am using any fuel tank is there inside the particular wing, whether I am using any propeller, or whether I am using any kind of solar panel over there. Now all those factors will come into the picture, right? Now then only we can fix that which one will be optimized. Okay. Now if
generally for
see,
yeah, please ma'am, please continue.
Yeah, see, there are certain kind of airfoils like KFM airfoils are there, which is just like that. Okay, so if you make the RC planes and all, they use like KFM airfoil, like we'll have the step airfoils. Okay, so again it depends. It's not necessary. This is on the NACA category I'm talking about. Okay, but if you see some Boeing aircrafts, they have their own patented airfoils. Okay, so if you go
Okay.
to that website called airfoiltools.com, okay, there you can see, just type Boeing and you can find that Boeing having their own airfoils. Okay. So they actually, I don't remember the name also. There are a lot many companies. They have manufactured their own aircraft and with their own patented airfoils. Okay. So all those things are existing, right? So this is a general
Uh,
category I said. Huh. Please continue.
yes, ma'am. How to go write the Campbell-Line equation of an airfoil, ma'am?
Campbell-Line equation.
The
So
mean Campbell-Line equation.
that actually there is a formula is there. Derivation is there. Y in terms of x of c. I think you are asking about that.
Yes, ma'am. Yes.
Okay, so that is having the derivation thing, right? So I have to look
Okay.
because I don't remember right now that equation. So once that, I think you will have some equation like x by c and some equation, then x by c square something. So how you
Yes, ma'am.
can get
By
it?
using that particular Campbell-Line equation, we can find out the moment and then the
Yes,
pitching
yes,
moment coefficient,
yes, yes, yes.
CMAC.
Yes, yes, you can find out that. And these are very easy because if you're plotting the if you're plotting the um, airfoil in a graphical method, you can easily find out what is x by c, and once you find x by c, you will find what will be the maximum y max. If you know y max, you will know where which point the movement will be expected. Theoretically, you can find out that will be the y. A change in interval of x and y, you can find out the movement also. Theoretically, it is possible to find.
Okay.
Hmm.
Okay, ma'am.
But only by means of graphical method. And nowadays, I don't think they prefer to use that graphical method. Previously, they used to use those methods. Nowadays, all they do, using computational methods, and now we have softwares. They use that. Okay, so usually they don't
Okay.
prefer to use that.
Okay, ma'am.
All right. So we were on here, right? Now come into this aerodynamic forces and moments. Okay, so this play a very important role, like aerodynamic forces and moments. These are why these forces and moments are taking, because of very two important factors. The first factor is due to the pressure distribution over the body surface, and second one is the shear stress distribution over the body surface. Okay. So last year, I think there was one question, they asked some couple of options, and they asked what it depends on the body forces and moments, right? So sometimes we have to be very precise with the basic things. Okay. All right. Now, when I talk about this pressure, that means pressure that normally acts on the surface, you can see the pressure that's normally act on the surface, and shear stress, which represent with a tau, which acts tangential to the surface. Okay, and the shear stress is formed due to the tugging action. This term is very important, is a tugging action on the surface, and this is caused by friction between the body and the air. This is caused by the body and the air. Okay. Now what happens, there will be that both the force, this pressure and the shear stress acting on the complete airfoil body. Now what will happen, it will causes some kind of resultant forces and moment. Okay, you can see the shear stress along the surface and pressure normal to the surface. Okay, normal to the surface, and due to this formation, what will happen, it will create, okay, it will create two different resultant forces and moment. The resultant forces are denoted by capital R. Okay, resultant forces are denoted by capital R. Now this is a resultant forces, right? Now this resultant forces, how it forms? Maybe it has some other component. So it having the two other components. This resultant will be splitting down into another components. One is the normal force component and another one in is that is a N, another one is a A. Okay, A is represent as an axial force. N is known as a, so this R is the, what I say, R is the aerodynamic force. R is the aerodynamic force. Okay, all right. So this aerodynamic force, resultant aerodynamic force, splitting into two different body forces. I can say R is splitting down into two body forces or axes, I can say. Okay, axis. These are the two axes. One is the normal force, okay, along the normal axis. Another one is the axial force in the axial axis. Okay, all right. Now when this happens, when this airfoil is inclined at some angle of attack, this is a relative free stream velocity, this airfoil is angled at some angle of attack. Now what will happen, this from the normal force, a lift and the drag will be generated. Lift and the drag will be generated. It's obvious because normal component of R perpendicular to the velocity is always the lift and parallel to the resultant component is a drag. So due to this, it will cause a lift and drag, and since it is inclining at some angle of attack, so we cannot say the lift will be the same when the change in angle of attack. So there will be some inclination, so that will be changing to the body axis as a normal force and the axial force. Now is that clear to all of you, this normal force and axial force? Please let me know.
Yes, ma'am.
All right. So basically what is lift and drag? Lift and drag is an, like when the perpendicular to the perpendicular to the free stream velocity, the velocity which produce upward direction will be the lift, and along the parallel direction with the free stream velocity will be your drag. But what happens, this airfoil is inclining at some angle alpha, that is angle of attack, some angle of attack. So what will happen, then this lift, the resulting aerodynamic force are no longer going to same as the lift and the drag, right? It will be shifting its nature. So due to this, it forms a body axis. Now what is this body axis? One will be happening on the normal axis, there is a normal force acting on the normal axis, and the axial force in the axial direction. Okay, so we can represent some kind of numerical formation like that. Okay, that means the angle between the axial force and the drag is alpha, and the angle between the normal force and the lift represent as alpha. Okay. Now if you resolve that, if you resolve geometrical relations, and we can bring out the lift equals to can I write, so since if I want to find the summation of all the vertical component equal to 0 and summation of horizontal component equal to 0. Now summation of vertical, what we have, lift. Okay, lift equals to, can I say, n cos alpha, what else we have, then here we have this perpendicular A sine alpha. Can I say like that? Can I write like that? Can I write? Because A,
Ma'am, it's minus sine cos alpha and
sorry,
ma'am, minus sine cos alpha plus a sine alpha.
minus cosine.
Yes, ma'am, minus sine cos alpha.
Why minus?
Ma'am, because it's in the direction of left, so after moving rightwards, it's become negative.
Alright. Right. Alright. Good. Thank you. So this. So what will I get here is, so plus you mean like this? Can I get like that? Here we will get
Ma'am, minus a sine alpha.
yes, this minus will be there. Minus, right? Equate to 0. Now similarly for the horizontal, what will I get? Horizontal, what we have along the direction of D, drag. So first D, then we have, just find it and tell me what you're getting. This will get again, all will get in terms of plus, right? All will get in terms of plus, that is here n sine alpha. Are you getting the same? Are you getting the same?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Yes. All right. Okay. Now we will move. Okay. Now let's consider the aerodynamic movement extended on the body depends on the point, okay, about which the movements are taken. Now we will see how the aerodynamic movements exerted on the body, okay, how the aerodynamic movement exerted on the body. Now first we have to see how this angle of attack depends on the movements, okay. So first we will consider, we are taking the movements along the leading edges. We will consider the movement is acting on the leading edges. Now what it says that the movement that extends to increase in angle of attack, okay, the movement that tends to increase the angle of attack are positive. That means if the angle of attack increases, that means we will get a positive movement. We will get a positive movement and we can possibly get an pitch up. We will get a pitch up. Now if the movements tends to decrease the angle of attack, if the angle of attack decreases, then we will get a negative movement. We will get a negative movement, that is a pitch down. That is the pitch down. Is that clear? So that means if we have the positive angle of attack, nose will be up, so the movements are also considered to be as taken as a positive. But here when it gets negative angle of attack, the pitch down, that will consider as a negative aerodynamic movement. Okay. Consider as negative aerodynamic moment. Now here we have lot many coefficients. Okay, so you need to remember this formula. What is lift coefficient, drag coefficient, normal forces, axial force, moment coefficient. Okay, moment coefficient. What is Q? Q is the dynamic pressure. Okay, dynamic pressure. Okay, remember. So you can expect a small problem from this particular formulas. Okay. Then again, pressure coefficient already have studied. Spring friction, please note down the formula. Tau equals to half rho infinity v infinity square. This is how you will get the spring friction drag. Now from this expression, what you can obtain from the expression from the spring friction, if the velocity and the particular flow stream velocity remains constant, if the shear stress increases, then definitely my spring friction coefficient will also lead to increase it. Okay, or lead to increase it. And whatever the formula you are seeing, it's all are satisfied for the two-dimensional body only. Okay, it is satisfying for the two-dimensional body. And remember one more thing, whenever we are representing with a capital C with a capital L, that means we are denoting for a three-dimensional body. It is denoting for the three-dimensional body. And if we have some kind of small letter case like small c suffix small l, that represents the two-dimensional body. This is three-dimensional body, this is two-dimensional body. And when we consider that, that means we are considering for the two-dimensional, means when we are considering the airfoil. 3D means we are considering for the V. Okay. Okay. So all right, now we have some basic layover, that the list of drag. Okay, so we have seen about the coefficients and all. Now we'll see the list of drag. Now these are the list of drag, the very basic list of drag, how these drags are formed, and how we can recover that, and what are the possible ways. Okay. Now pressure drag, induced drag, screen friction drag, wave drag. Okay. Now what is pressure drag? How does pressure drag form? Now before that, what is drag? Drag is a resistive force or which obstruct the body to flow for to move forward. Okay, it creates a resistive kind of force which avoids the particular body to propel or move forward. Okay, which resists the body. Okay. And that particular phenomena is called as a drag force or the drag. Okay. Now this can be happens on different kind of consequences. Okay. Another kind of, I have forgot to add on, is a interference. Right. Okay. So pressure drag, when it forms and where it causes a majority impact on an aircraft. Then what are the possible ways? First, if the body is blunt, it's over blunt. So if over blunt, it will form an wake formation. So it will causes an adverse pressure gradient. So due to that, again it will form a pressure drag, right? So you have to form a streamlined body where you can reduce the pressure drag. Okay, so using the better streamlined body, you can decrease the pressure drag. What is induced drag? What it makes to form the induced drag? What is induced drag? Mostly it happens due to the formation
Ma'am,
of
could you please explain it one more time?
which one, dear? For the pressure drag?
Ma'am, pressure drive. Yes, ma'am.
Yes, it is just
How to reduce it?
huh. We can see just for an example, a good example. Let's take a blunt body or like a circular body and a airfoil. Okay, so if same amount of flow velocity undertaken by this particular different objects, okay, so what will happen in this kind of circular object? There will be some kind of wake formation, and unlike there will be a streamline flow at that particular airfoil, right? There will be a streamline flow, right? So here, due to the formation of the wake, what is happening? Actually the wake helps to create a reverse flow. As you remember, we have seen in the boundary layer, it helps to create a reverse flow, and this reverse flow, what it does, it increases the pressure gradient, that is dou p by dou x is increased. So when it is gradually increases, that is the pressure gradient. That means pressure is increasing with change in some particular respective distance. So this causes the obstruction, okay, disturbance. This kind of disturbance is called, comes from the pressure drag. So how you can avoid? Obviously you have to make a streamline pattern to avoid such kind of pressure drag, right? Okay, now induced drag we formed, it's mostly based on the formation of vortices, okay, vortices at the tip of a wing. Okay, so if I look an aircraft from the rear end, okay, from the rear end, let me draw. So this is the root section, this is the free stream velocity. Okay, now what happens? Bottom we are seeing from the top view. Okay, top view. Now bottom we have the high pressure, top we have the low pressure. So the vortices form in this way, right? Now similarly here the vortices form in this way, right? Did you got the curves? So similarly this vortices creates a kind of drag. Okay, so this along the surface, along from the root to the other the tip. So here the vortices generation will be much less as compared with the tip where we have the majority of the vortices are generated. So how we can avoid this induced drag? This drag can be reduced by implementing a concept called winglets or wingtip. Okay, so they will use an additional surface, right? So winglets and wingtip. So using that, the main thing what they improve is they increase the span length or increase the aspect ratio. Okay. Now what is aspect ratio? Again I will come to the part what is aspect ratio and how to classify that aspect ratio. So by increasing the aspect ratio we can decrease the induced drag. Okay. There is a mathematical expression is like this: the coefficient of induced drag equals to CL square by pi EAR. Okay. There is some kind of formula like this. Okay, so if the CL is constant, right, if I am increasing the aspect ratio, then that means I can reduce the induced drag. If what it says that if I am increasing the aspect ratio, that means I can decrease the induced drag coefficient. Okay, this is one case. Now if another thing, if I am keeping the constant, if I am keeping my aspect ratio constant, then by increase in my CL, I am also increasing the induced drag of that particular induced drag. This is the significance from this formula. Next comes skin friction drag. Skin friction drag, again the same. You have to create a very polished surface, right, to decrease the shear stress, from the surface. So previously I have shown you one formula how to decrease the shear stress, right? That was, this is the formula. So if you decrease the shear stress, you will automatically decrease the skin friction drag. Okay, skin friction drag. Then next is a, before coming to wave drag, we will move to another one, is a interference drag. Okay, interference drag. Now what is interference drag? Interference drag is, but the name you can understand, it is interfering. Now how these things are interfering? A very best example is a biplane. Okay, what is biplane? Consider this is a front view of your aircraft, and previously if you have seen Wright brothers aircraft, that is a biplane. So you have two wings, right? You have two wings. Now what happens in the wing? Obviously the bottom you have the high pressure, then top will have the low pressure. Now again, since you have another wing, we have the another high pressure, here we have the low pressure. Now here what happens, in this gap, in this zone, right, in this zone, there is some interaction of the high pressure and low pressure, right? There is a huge interactions of this high pressure and low pressure that creates a huge drag. Okay, that creates a huge drag, that is called as an interference drag. And from there, that's why most at the present aircraft has been converted in a monoplane. Monoplane means having only single wing, so that's why this concept has been obsoleted. This concept has just closed. Okay, so we no longer use this concept called biplane, though it will increase the lift because the surface area increases, that means the lift will be more, right? But this is the major problem, interference drag. So to overcome that, we have the, at present we have the monoplane. Okay. Now coming to the wave drag. Wave drag is nothing, we only consider when the flight is and more than more than Mach 1 or the supersonic region. Okay, so when the pressurization occurs in the particular foil, airfoils and all, so instead of talking in the pressure drag, we just name that is a terms of wave drag. That means when the formation of shock waves. What is shock wave? It is one kind of pressure boundaries within the particular region. So that is renamed as a wave drag. Okay. So you can see, you can also expect that they will give you some kind of figures, and from the figures you have to understand, or you can have to nomenclaturely you have to align which one will be having the highest drag or the highest peak of lift and so on. So these are some of the case studies, that drag coefficient for various kind of aerodynamic shapes. Okay, So you can see first we have the plate, then like cylindrical diameter, then streamlined body, Then the streamline, the cylindrical diameter, which is just 1/10 of the previous one, and another we have the cylindrical body but different kind of Reynolds number, variation of the Reynolds number. You can see the different Reynolds number. So what is the CD value? Okay, what is the CD value? So from here what you can understand that though the main thing is here is cylindrical diameter, just look into it. Now when you are increasing the Reynolds number at this cylindrical diameter, we can find that drag is reduced. Okay, this is one of the important thing to see. Now looking here, though you are reducing the cylinder diameter and keeping almost equivalent amount of Reynolds number, there is some negotiable change in your coefficient of drag. There is a negotiable change in the coefficient of drag. That means what it helps to decrease the drag neither by the shape, it is definitely by the shape, it is irrespective of the size. It is irrespective of the size, but yes, the CD is definitely depends on with the Reynolds number. CD, that is a coefficient of drag, that it is depend, one of the factor that it depends on the Reynolds number. Okay. Now similarly we can see based on this particular consideration how it affects with the screen friction drag and the pressure drag. Okay, how it is affecting the screen friction drag and the pressure drag. So I'm quite sure that they are going to ask such kind of thing, like from here this particular case study, different kind of case study, you can understand which among this particular cross section will have the greater CD and greater screen friction drag and the pressure drag. Okay, so you can understand from here that this in this E, the graph E, diagram E, when we have the Reynolds number flowing over the circular cylinder, right, the pressure drag is forming more as compared with the this one, as compared when the Reynolds number is less. So this also you can find over here. So when the Reynolds number is more, right, your pressure drag is getting larger. Okay, but one thing is another very sure is that the point of flow separation, is getting delayed. The point of flow separation is getting delayed over the when the Reynolds number is 10 power 7 over here. So these are the significant points that you have to look after this particular figure. Okay, so you have to know when and how the screen friction drag will occur and pressure drag will be more based on the different kind of Reynolds number, though their cross section is getting same. Alright, so there are certain strategies. Okay, in a circular cylinder, when the Reynolds number moving or the flowing within the range of 0 to 4, such kind of flow is known as a Stokes flow, right? When it is beyond, when the flow is beyond your 3 into when it is 4 to 10 power 3, right, and the flow creates something like this, you can see, right, the vortices formation is something like that. It is not separating, but it is creating something, the vortex sheet, it's called as a, this such kind of flow phenomena occurs when it is between 40 to 10 power 3 of Reynolds number, we get this Kalman vortex sheet. and beyond that the flow is haphazardly spills around, and here you can see more than that what happens. Okay, more than that what happens. Alright, so they can give you the graphical representation and they can ask you find out the best out of it. So what Reynolds number, what are the possibility of the flow over a circular cylinder, you must know the phenomena. So you can remember the first 4. In the B point, when it is in between the 4 to 40, so it will create an kind of oval, okay, dual oval, you can say it will create an dual oval, okay, dual oval at the rear part of the cylinder, circular cylinder. And the first one is the stroke flow, third one we have the carbon sheet vortex, and the fourth one is a spilling formation. Okay. Now before moving to center of pressure and all, you should know. Alright, so here I get that. Okay. Alright. So let's see how this airfoil, or I can say how this CL with angle of attack will change in angle of attack, and what are the performance occurs in this particular airfoil. So in this figure, but you can see that first, second and third. Okay. So when we have very low angle of attack, what happens? Gradually lift will takes place. Lift will slowly increase. As we increase the angle of attack to the highest, lift will be the CL max. See here, the CL is in small letter, not in the capital letter. That means this is representing the CL of the airfoil. Now after this point, it reaches to the maximum angle of attack. Beyond that, it started to increase the angle of attack. Suppose consider this point. What will happen? It will start to stall. And what is stall? That means there will be a flow separation over the airfoil. Flow separation in the sense there will be a reverse flow, high pressure zone occur over here, high pressure zone occur over the surface of the particular surface of the profile. That can lead to the structural damage of the profile. If the structure is not well defined with an airfoil, it will cause more turbulency. If it causes more turbulency and leads to an structural instability, okay, and it can also lead to dive the aircraft, or it can lead to get spinning of an lot many flight controls are there. It can also lead to spinning, or it can lead to Dutch roll and so on. So lot many instability factors or instability modes can take place. Okay. So always the pilot, when they are flying, so they always maintain that not to fly or not to lead to a very increase in angle of attack. So always they will move in the safer zone. So this is the safest zone. In one of the gate question, they have asked that they have given lot many graphical representation, and they have given the leveling of the points or the zone. So they have given like which among the places will be the safest for the flight to land successfully. Okay. So we never want the majority of the points they have given along these points, okay, along these points in the stalling region. So this is the red marking where I am making. These are the stalling region, that is these are the danger zone. The flight should, once it moves along here, it will start to stall. Start to stall means it will lead to an instability. Okay, so again it is up to the pilot whether it can whether by using other control surface they can lead to in right direction or not. Okay, so preferably they don't prefer to use in this red color zone. Okay, always they prefer to move in the safest zone. So you must know which is the safest and which is the best suitable range of flight. So here there was animation which is not working over here, but you can see the flow visualization, how the wake formation takes place right here. So again you must understand how this flight changes with your increase in velocity, how the lift varies with increase in what is the relation between the flight speed and the coefficient of lift. Okay, now here you can see the coefficient of lift. Do you think it is for airfoil? This is for the entire flight. Okay, this is for the complete aircraft they are talking. It is not only for the airfoil. So what you can see from this graph, as we decrease the angle of attack, right, what in which direction they are showing the angle of attack, as we decrease the angle of attack we can maximize the increase the velocity, more you need to increase. Here we have high, here we have low. So more the angle of attack, more it will leads to an stalling region, and the point of stall it begins where we'll have the maximum CL. Okay, so if they ask you to find out the CL for an or CL max, that means you have to use the V stall. That is, what is the formula? L equals to half rho V square S CL. This is the general formula. If they ask to find CL max, we can consider the lift at the steady level flight. Lift is equal to weight equals to half rho V stall square S CL max. Okay, that time you have to use this equation to find out either of the parameters. Okay. Now again looking to the case of the drag coefficient. Now this is a drag for the overall drag of an aircraft. Okay, now how it depends? It depends on the aerodynamic shape. If we have the low aerodynamic shape, what is happening if you have the high drag aerodynamic shape? That means if the aerodynamic shape is not that well optimized aerodynamically, the drag will be higher. If you are having the better aerodynamic shape, then the drag will be lower. Okay, that is a statement you can build up from here. Not only that, you can also obtain the maximum speed that it can obtain by this high drag aerodynamic shape will be much lesser as compared with an low drag aerodynamic shape. That means, for an example, if I have an airfoil, this is for the airfoil and this one for the circular cylinder. Now circular cylinder will be having the high drag as compared with the airfoil section. Now if the shape I am flying at V infinity, that is a free stream velocity, what I can attain, that V max will be attaining highest. That means if this is the v infinity is going, if this is a 100 and this is 200. Okay, for an example, this 100 meter per second, 200 meter per second. Now which one can attain the better speed, better maximum speed? Yes, it's obvious that airfoil can lead to a better maximum speed as compared with the circular cylinder, because the high drag aerodynamic shape cannot attain a maximum speed as compared with a low drag aerodynamic shape. Okay. Second thing, if you see, another important thing, they have used C minimum. The height of C minimum is much less as compared with the high drag aerodynamic shape. This is for the CD minimum for high drag and this one for an low drag aerodynamic shape. So this is again comes under the conceptual point of view. So from this graph you can figure out so many factors. First factor is how this angle of attack stalling parameter varies. Okay, then how this aerodynamic shape can leads to an increase in the maximum speed it can attain, right? Then is a CD minimum factor, CD minimum factor. Next, similarly we have another strategies. How now they have combined CD with velocity, that is a aerodynamic efficiency. Okay, the L by D is also known as an aerodynamic efficiency. Okay, aerodynamic efficiency and with respect to the flight speed. Now what you can see over here, aerodynamic efficiency, as you increase the flight speed, you need to increase the CD value, CD, or I can say CL by CD value. Okay, either of that, I can say CL by CD value or L by D value. So L by D value keeps on increasing. Once it reached the maximum CL, that means L by D value or CL by CD value max. Okay, it, though we are increasing the velocity, what will happen? It will leads to decrease in CD. It will leads to an decrease in CD. Okay. This is one of the significant point you can find out from this particular graph. Okay, this is what happens. The aerodynamic efficiency increases till the maximum. After the maximum, though you are increasing the velocity, that aerodynamic efficiency falls. Okay. Next, what it represents, that it is a CL by CD graph with angle of attack. It also represents the same, almost the same pattern. So once it reaches the maximum point, obviously, as you know from the angle of attack with CL, what happens once you reach, that means this is the maximum point. Beyond this, it will leads to stall, right? Beyond this, it will lead to stall. Similarly, though you are increasing the increase the velocity, this is the stalling zone. This is the stalling zone. The velocity, however, the velocity is increased, but it will keep on decrease the lift to drag ratio. Okay. Is that clear to all of you?
Yes, ma'am.
All right. So let's see how this okay. I just get one case study. Alright, so again, when we talk about this aerodynamic efficiency, you have to know how this aerodynamic efficiency changes with, you know, the same thing you can see, right? So if you see the transport aircraft, okay, transport aircraft whose L by D will be ranges from 15 to 20. Okay, if you look for the fighter aircraft, okay, the fighter aircraft, that if you see the L by D will be within the 10, within the score of 10, okay, within the score of 10, right? So here I have, so this is the L by D actually. This is in terms of Mach number. This is the L by D in terms of, here in terms of Mach number. So you can see once the more the Mach number you go, lower gets the value. You can see more the Mach number you go, it ranges within kind of 10, right? And within this, within the Mach 1, you can see how widely it ranges. Now if it is less than 0.5 Mach number, you can see it is ranging within 25 to even 70. Some are ranging within 25 to 70. Beyond 0.5 to 1, it is ranging from 35 to, you can say 15, even you can lead to 35. Okay, then when we have the Mach number more than 1 and beyond, you can say it is ranging within from 5 to 10. More than Mach 1, it is ranging 5 to 10. Okay. This is another strategy you can obtain from here. So okay. Now again, this statement is very important, Kutta-Jakuski theorem. Okay, what is Kutta-Jakuski theorem? Okay, it is a two-dimensional body and which is directly proportional with the circulation around the body. So what it says that the lift per unit span is equals to the density, velocity, the product of density, velocity and the circulation. Okay. So again you can expect a problem from this statement, Kutta-Jakuski theorem. There are small statements, yes. So this is what I was talking about, how the speeds varies from each range to range. Okay. Now at present it is going to 21%. Okay. At present it is going to 21%. Now there are many types of wing platform. Okay, wing platform. You must know the name of the wing platforms. Okay. So this we will look into that upcoming session. Maybe it's a very lengthy topic. So rectangular wing, what are the advantages, disadvantages of lengthy this taper wing, then okay, delta wing, then where we use monoplane, biplane, triplanes, okay, which wing configurations, aspect ratio, yes. So what is aspect ratio? We were talking about aspect ratio. Aspect ratio is a ratio between the square of the wingspan by the wing area. Okay, so there is a difference between wing area and weighted wing area. Okay, weighted wing area. Do not get confused with the weighted wing area is different than the wing area. Okay, so here we are not dealing with any sort of weighted wing area. Weighted wing area means, suppose you have one square, you have one kind of rectangular object, and the flow is moving over the rectangular object. The weighted area means when the flow comes, it hits over here, then it spills over this particular profile, particular object. That means where this fluid has been, or I can say in other words, the complete perimeter of the object, and the complete perimeter area is called as a weighted area. But here when we are finding the aspect ratio, we are not using this weighted area, that where how much area the fluid has been touched along the profile, right? We are just taking weighted area means, if I look in the top view, it will just look like an rectangular to me. So I will just take this particular area, not its the circumferential area, right? So whenever we are considering this aspect ratio, we are not considering the weighted area. Okay, so now this is the formula is only applicable when it is a monoplane. Suppose in the question they have asked you for the biplane and triplane, what will be the formula? Then you have to use this formula, that is aspect ratio equals to 2b square by s, and for the triplane you have to use 3b square by s. If quad, that means you have to use 4b square by s, if in case of quad. Okay, next important concept in this aspect ratio, it says that for 3D wing means 3D means it's for wing, 2D means it's for the airfoil, the cross sectional or the wing cross section. Okay, so it says that compared with the airfoil, the wing lift will be reduced. That means the CL at 3D will be less as compared with CL at 2D. Okay. Next, as we increase the aspect ratio, that which way the aspect ratio is increases, right? So gradually, if the aspect ratio is more, that means CL will also be improved. So you can see, as we increase the aspect ratio, the CL will also be improved. Okay. But one more parameter, CL will be improved, but the stalling angle will be appearing more early as compared with the other one. So if I consider which one will be having the more stalling angle, so here if I consider this is a stalling angle, here this is a stalling angle. So which one is getting delay? It's getting delay for 3D wing, but reaching early for the 2D wing, right? This is one of the another important factor. Then already we have discussed this point. Okay, now here another how this aspect ratio varies. Now based on the different kind of aircrafts, so you can see glider where we have the maximum amount of aspect ratio, least we have the hypersonic aircraft, missile, okay, tactical missile we have the lowest one, next we have the hypersonic, Then in between we have the transonic, right? Then we have the highest peakest is the glider. So you must know how this aspect ratio varies with the types of aircraft. When I talk about transport, we know the what is the speed region between the transport, and when I talk about a fighter also, you should know that. Okay, fighter means always the Mach greater than 1 to 2. Okay, hypersonic Mach then 5. So how this Mach number and the different kind of aircrafts varies with a different kind of aspect ratio. This is another case study. You have to remember these parameters. So I can say tactical, then hypersonic, then we have the supersonic fighter, then we have the transport region part, then fifth one we have the sailplane or the glider. Okay. Then another important point is a taper ratio. What is a ratio? What is that taper ratio? It is a ratio between the tip chord with the root chord, and how to find in terms of span to span area, wing area with a span. Okay, this is a formula. You have to remember this formula, right? Then we have mean aerodynamic chord formula. Okay, CF plus 2 plus okay. So this is the formula for mean aerodynamic chord. So they can expect you to ask you some kind of MCQ from the small problems, small equations. Yes, another important last topic, okay, so is that geometric twist and aerodynamic twist. Okay, now what is the difference between geometric twist and aerodynamic twist? Now twist means you know that from the root to tip there will be some kind of twisting angle. Okay, now geometric twist says that before that I will just explain what is aerodynamic twist. Aerodynamic twist is that both in the root and the tip section we will have a different kind of airfoil section. Suppose in the example you can see here, in the root section you have some kind of NACA airfoil 634221. Okay, 634221, and in the tip we have NACA 0024, right? So these two different kind of airfoil when we place in the different kind of root and tip, it will create itself is an automatic twist. Okay, this twist is called as an aerodynamic twist, or in other words I can say the different kind of airfoil section in both the root and the tip which helps to make the wing to twist is called as an aerodynamic twist. Then the opposite of the aerodynamic twist is a geometric twist. There what happened in the geometric twist is both the tip and the root airfoil remain same, but the angle of attack changes. In the tip section. Okay, if it is in the negative, you can say negative angle of attack, we get as a negative twist. If it is a positive angle of attack, we get as a positive twist. But here geometric twist, what happens, both the series, whatever the airfoil series you are considering, it remains same throughout the section. Okay, now
Excuse me, ma'am.
yes, please.
Can you explain the geometric twist again, please?
Yeah, sure. What happens in the root? In the root section, the suppose we are using NACA 2415. Okay, this Naka airfoil is constant. I am not changing my airfoil. The cross section in the root and the tip is same, but don't worry about the chord, root chord and tip chord, but the airfoil section is same. What I am doing in the tip section, I am keeping a negative angle of attack. Okay, and the root remains same. Root remains 0 degree, and the tip I am making the negative angle of attack. Such kind of configuration, wing configuration, will give a negative twist wing. Okay, and if I make a reverse pattern, suppose I am making the tip positive angle of attack, right? You can see the figure, positive angle of attack, which will give a positive twist. Okay, in other words, they can also called as wash in, and in case of negative twist, they call as a wash out. Okay. Clear? Now before
What's the
winding,
significance of this shout and wash in, ma'am?
significant is that why they use that wing twisted angle, because to some kind of they improvise the stability, and their ranges you see very negotiable ranges. It's from 3 degree to -5 degree. Okay, and if you see for mostly the fighter aircraft, mostly they prefer to keep at 0 degree, but whatever the case study which I have made, mostly they prefer to use a washout. They have the negative angular twist. How much? -1, -3, -2.2, such kind. So what? How they find out this parameter? They find out this kind of computationally. They have analyzed that in a software. So they have found out
How the
optimized
stability
one.
is being, how the stability is being having the washout, ma'am?
Stability. See, what this airfoil does, this airfoil helps to increase the lift, produce lift. So do you think it is only helps to produce lift? It also acts the center of pressure. It is also having the aerodynamic center. It's also having the center of gravity. So when the center of gravity comes into the picture, then you have your center of pressure. So based on the wing loading formation, the shift of the shift of this static margin will also vary, right? So that more detail, that why this twist angle play a significant role, you will understand more in detail when you will see the flight dynamics. Okay, when you will see the flight dynamics, especially the static margin. I think already have studied the static margin, the neutral point, right? So what you do is, if you ask that how I can say so clearly, that it will be helpful for wash in and wash out. Okay, now when you are designing any aircraft, okay, so what you will do, you will have some initial assumptions initially, right? So with considering some assumption, you will proceed, but what you will do in the later part, you will keep on doing iterations. Okay, in the iteration, if you see, or you can computational method, if you see that this particular wing design is not giving the effective amount of lift which you require, then what will you do? You will see, you will vary everything, right? You will change everything. You will see how much angle of twist. Now I am changing this much. Let me see what is the profile I am getting. Then again you will change, right? So gradually, experimentally, they keep on doing like this, and they finally optimize the parameter. Finally, they find out this parameter. Okay?
Yes, ma'am.
Okay. And simultaneously, that is initially. Again, what they will do? They will go for the flight testing, and there it has to satisfy this consideration, right? It has to balance that. Then only it will be fruitful, right? Okay. So, any questions? Any other questions? So here let me wind up the session then. If you have any question, please